everyone. Today we are taking a look at AP Chemistry 2.1, Types of Chemical Bonds. In order to understand chemical bonds, we should probably review a little bit about electronegativity. Electronegativity is something that is covered in Unit 1 when we talked about periodic table trends. So just to review, it's a measure of the ability of an atom or group of atoms to attract shared electrons. Why is this important in bonding? Is because whether the electrons are shared or transferred tells us what type of bond it is. Also, it's not always an equal sharing. This can be explained by Coulomb's law, as can most periodic table trends. So remember, Coulomb's law is this guy. And basically, we don't need to use the equation to calculate anything, but we need to understand what it means. So Q1 and Q2 stand for the charge of the ions or of the particles. And because it is in the numerator, if you increase charge, you will increase the force of attraction. In the bottom, we have this r squared value, and that is the radius, the distance between the radii squared. And so this number, if you increase it, it is going to have an inverse relationship. So if the denominator gets bigger, I am going to decrease my force of attraction. So, electronegativity, the ability of an atom or group of atoms to attract shared electrons. This can be explained by Coulomb's law. Fluorine is the most electronegative atom, and the reason for it is because it has a small radius, so it's going to have a large F value, and it has a high nuclear charge. So it has that perfect combination of having both a small radius, so R is small, and Q is big, therefore F is very large. So fluorine is the most electronegative atom that we have. Now, one of the things about electronegativity is that we can actually, there are numeric values that go with each of the numbers or each atom on the periodic table. So for most periodic tables, fluorine, the highest electronegativity is going to be at 4.0. And then every other element on the periodic table is going to have a smaller electronegativity. That's important because one of the things that we can look at to determine what type of bond we have is the electronegativity difference. So if I look up the electronegativity values and I have a very large difference in electronegativity, a large difference in electronegativity is going to mean that I don't actually have a sharing of electrons at all. I have a transfer of electrons. And this is what we call an ionic bond. So if A transferred the electrons over, then A would be positively charged and B would be negatively charged, and it's that positive and negative that attract each other. That's what makes an ionic compound. If the difference in electronegativity is very small, then we consider this to be an equal sharing of electrons. And we call this a nonpolar covalent bond. Covalent has two different types. It can be nonpolar or it can be polar. Here in this little picture, the colon is supposed to represent your electrons, and they're right in the middle between A and B, which means that neither A nor B has a stronger attraction. I like to think of it as a tug-of-war. If A is in a tug-of-war for the electrons with B, this would be the rope, and then this would be the little knot that they're trying to pull to one side or the other. And with a nonpolar bond, we're at a stalemate, meaning no side is winning. And this happens when we have an electronegativity difference that is really small. And on most accepted values, that's going to be a difference of less than 0.5. It usually happens when carbon is bonded to hydrogen. That's generally considered to be nonpolar. And then anything that's bonded to itself. So for example, if I had two oxygens bonded to each other, it would be like twins in a tug-of-war. No one wins. Then in the middle, we have this in-between area where it's not big like an ionic bond, and it's definitely not small like a nonpolar. And that's where our polar bonds live. This is going to be an electronegativity difference from 0.5 to 1.7. And what this means is it means that one of the atoms, either A or B, in this case it's going to be B, is really electronegative. And it actually is winning the tug of war. You see those colon, I'm highlighting them there in the blue, it is shifted towards B. And so what that means is that B is more electronegative than A is. And what happens is this B, because it pulls the electrons closer to it, it develops a partial negative charge. And if all of the electrons are being towards B, that means A is going to have a partial positive charge. And we call that a dipole. And that affects how that molecule will behave. Again, it seemed a little odd at first when we brought up electronegativity, but electronegativity really helps us what type of bond we're going to have. Is it going to be ionic? That's going to be a large difference in electronegativity. Is it going to be nonpolar, which means small difference in electronegativity values, or polar, which is kind of the in-between. So if you go to a website like ptable.com, you can actually get electronegativity values for every single element that's on the periodic table. And all we would do is subtract those. So for example, I just looked up that oxygen's electronegativity value is a 3.4. And so if I had a fluorine-oxygen bond, that is definitely going to subtract. If I subtract 4 minus 3.4, I get a value of 0.6. And so that means that I can classify this bond between them as a polar covalent bond. If I subtracted them and got a number less than 0.5, then it would be nonpolar. And if it was really large, then I would get a polar. And if it was really large, I would get an ionic bond. Now, let's deep dive a little bit into each of these subsections, because not only is it important to understand how these bonds work, but they're also going to ask us to explain different aspects of the bonds. So an ionic bond usually occurs between a metal and a nonmetal. And the reason we know that is because that's going to give us the biggest electronegativity differences. What happens is our metal will send electrons over to the nonmetal. The metal becomes positively charged. The nonmetal becomes negatively charged. And this attraction is what holds them together in an ionic bond. They are stronger when the charges are larger. For example, if I had something that formed a +2 ion and a -2 ion, like calcium with oxygen, that's going to be a stronger bond than if I had sodium with chlorine, with both of them having a +1 -2. We can actually look at the charges to rank the strength of ionic bonds. So the charges are small, it's not going to be as strong as if I had something that had a larger charge difference. If we have small ions versus large ions, that will also increase the strength. An example there would be if I had something like lithium chloride. Lithium on the periodic table is a much smaller one compared to sodium. And so lithium chloride will have an increased force of attraction, therefore a stronger bond, because lithium has a smaller radius. Again, we're still always going to be coming back to Coulomb's law to explain some of these things. You'll get sick of hearing about Coulomb's law. We talk about it so much. Now, some things about ionic compounds and their physical properties. They tend to form what's called a lattice structure. A lattice structure is alternating negative grid. And this is called the lattice. And if the first one was positive, then it would be, this row would be negative, so on and so forth. And these go in 3 dimensions. So I have atoms of each one going back and down, and it forms this 3D lattice structure. They do tend to have high melting points and boiling points. They are hard and brittle. They do conduct electricity when they're dissolved or when they're melted. So when you dissolve an ionic compound, those ions that are locked in place in this lattice structure, the lattice structure dissolves. And so if I look at a beaker where I have them dissolved in water, this is a poor drawing of my beaker, then they are actually separated from each other. And that's what allows for the conduction of electricity. And they tend to be good insulators when they are in their solid form. Another type of bond that we haven't talked about yet is called a metallic bond. A metallic bond is very similar to an ionic bond, except instead of having alternating negative, we only have positive ions. And a metallic bond can be made of just one type of metal, or it can be a mixture of metals, and we call that an alloy. The metallic attractions are due to multiple metallic cations, that's these yellow plus guys, being attracted to a delocalized sea of electrons. These pink dots are representing our electrons, and the thing about metallic bonds is that the electrons are not staying in place. They're constantly moving all over the surface of this. So what that allows for is the cations to still be attracted to each other, because if these positives get too close, they'll repel. So this delocalized, the fact that the electrons are free to move about, is what keeps it together. And we can look at strengths of metals as well based upon how big the ions are and how many valence electrons they have, because more electrons means that the sea of electrons is going to be bigger. And so we either call this delocalized electrons, or sometimes you see it called a sea of electrons. They're just moving around like ocean waves across these cations. This allows the conduction of both heat and electricity. They tend to be malleable and ductile. Malleable means it can be hammered into sheets. Ductile means it can be stretched into wires. They tend to be shiny, and a fancy way to say that is that they have luster. When they form with oxygen, they tend to be basic in nature. So for example, if I had something like magnesium with oxygen, MgO, that is going to form something that's chemically a base. And then they tend to lose electrons when they form cations. All right, next, let's take a look at our covalent bonds. We are going to be doing deep dives on covalent bonds for a lot of this unit, but just to introduce them, they do come in two flavors. One is a non-polar covalent bond, and notice that the shared electrons are, notice that there is no lopsidedness in a non-polar covalent bond. The electrons are moving equally around the atoms. And again, this would be like if I had a carbon bonded to a hydrogen, that has a very small electronegativity difference. Or if I had something bonded to itself, that will also give a very small electronegativity difference, which is where we get our non-polar covalent bond. But when we have something that is polar, that means that there is not an equal sharing. So in this example, the electrons are being pulled more towards the blue atom. So let's say, for example, this was H. Well, fluorine is way more electronegative, and so the electrons are actually being pulled this way towards fluorine. And what that does is it gives fluorine's side of the molecule a partial negative charge. And that is the way that we show a dipole, is to put this little Greek letter and then the negative sign. And then because they're being pulled towards fluorine, that means that the hydrogen end becomes positive. And so sometimes you see dipole arrows drawn like this. Or, like I mentioned before, we can use this little Greek symbol and a positive sign to show that this is the positive side of the molecule and this side is the negative. All right, so some examples here of our introductory section in Unit 2. It says, how can Coulomb's law be used to predict electronegativity? And this has to do with our nuclear charge and a small radius. So I would say something like, if an atom has a small radius and a large nuclear charge, it will have a high electronegativity value. And I like to abbreviate electronegativity EN. If an atom has, and the opposite is true. So if an atom has a large radius and a small nuclear charge, it will have a low electronegativity value. So now we have, is the electronegativity difference large, small, or nearly zero for each of the following? So a nonpolar covalent bond, this is a very small difference in electronegativity that goes from 0 to around 0.5. A large difference in electronegativity is going to be our bond, and it's going to be greater than usually 1.7. So I would say that this is large. And then our polar covalent bond is going to be between 0.5 and 1.7. And they're asking for large, small, or nearly zero. This one is like the middle ground, so I'm just going to call that middle. And then both small / nearly zero would describe this one. So there's not really a indicator here that I feel comfortable giving to polar covalent bonds. All right, so now we have, how would we classify the following bonds? I'm going to jump around a little bit. I'm first going to take a look at D, and that's because both of those are metals. And so if both of them are metals, I can call that, I know that's going to be a metallic bond. And again, each of these, we are going to do a little bit more in subsequent sections about these. This is just to introduce it. And then how do I know that this is going to be a metallic bond? Is because I have both metals and nothing else. Next, I'm going to come up to letter B, because letter B, automatically I recognize that I have a metal plus a nonmetal. That to me makes me think this is ionic, but just to be on the safe side, we could also check the electronegativity difference in both of them. So calcium's electronegativity is 1. Oxygen from earlier, it was 3.4. So if I subtract those two numbers, I get a difference in electronegativity of 2.4. That does fall in the greater than 1.7, which tells me that this is going to be bond. So I'm going to say it's ionic. And my reasoning is that the electronegativity difference, and sometimes we use the delta, that's a triangle, to describe a change in electronegativity or a difference in electronegativity, is 2.4, which is greater than 1.7 and in the ionic bond range. Next, I'm going to look at letter A. I've got bromine bonded to bromine. So both of these are nonmetals. And because they're both the same atom, I believe that this is going to be nonpolar. Again, my justification is that the difference in electronegativity will equal 0 because they're the same atom. Same atom means same electronegativity. And then finally, I wrote a little bit big here, but the HN, this is going to be my polar covalent bond. And how do I know that this is going to be a polar covalent bond? Is because I would look up the electronegativity values for each of those. Hydrogen's electronegativity value is 2.2. Nitrogen's electronegativity value is 3.04. So if I subtract those, 3.04 minus 2.2, I get an electronegativity difference of 0.84, which does fall in the range for a polar covalent bond. All right, that is 2.1, Introduction to Types of Bonds. Again, we're going to be looking at a lot of the details surrounding each of these types throughout the unit. So if everything seemed a little overwhelming today, don't worry. We are going to be covering all of this as we move forward.